Hello, good morning. Characterization of nanomaterials using X-ray diffraction. A Skinner's question. XRD techniques is an important tool for the study of crystal structure and atomic spacing. XRD is based on constructive interface of nanochromatic X-rays on a crystalline sample. The crystalline sample acts as 3D diffraction for X-ray wavelengths similar to the spacing of planes in a crystal lattice. The interaction of incident X-rays crystals sample produces constructive interference. If the conditions of the Bragg's law, that is 2D sine theta equal to n lambda, is satisfied, the interpolar distance lambda wavelength of monochromatic X-rays beam theta incident diffracted scatter angle. See in this example, this is the crystal surface layer, distance between the layer. This is the incident ray and diffracted. These are the 2 rays diffracted from the these 2 points of the crystals. So we have to perpendicular draw from the this point let O to X perpendicular and O to Z and perpendicular, and this point is the Y. And so if this is the perpendicular, this is the 90-degree angle, or the 90-degree angle, and this is the right angle triangle. This is the perpendicular, and this hypotenuse, and this base. So let us consider two parallel X-rays, 1 and 2, are made incident on two different planes of the crystals at the incident angle theta. The total path difference between the two X-rays that escape from this crystal is given by the path difference xy plus yz. Path difference xy plus yz. Total path difference from the right angle triangle OXY sine theta OXY sine theta base over hypotenuse, base in the triangle OXY, base OXY, base XY, and OY is the hypotenuse. This is the perpendicular. So sine theta equal to XYD, from simplification, XY equal to D sine theta. Similarly, in triangle OYZ, sine theta equal to YZ over OY. So YZ equal to D sine theta. So that path difference XY plus YZ D sine theta plus D sine 2D sine theta, a constructive interference that results in the bright band Bragg's peaks is observed when the path difference between the diffracted X-ray equal to the n lambda equal to 2D sine theta equation 1, where lambda is the wavelength of the X-ray and n 1 to 3 called order of the reflection. The equation 1 is called Bragg's equation or law. These are diffracted X-ray from various planes are detected, processed, and computed. All the possible diffraction direction of the crystal's lattice can be attained by the scanning the sample through a range of angles to theta. The diffraction peaks are the informations of different orientations of the planes having the different Miller indices SKL. The Miller indices of planes has direct relationship with d spacing of the planes. The crystal can be identified the conversion Miller indices of the diffraction peaks to the d-spacing because each of type crystal has set of the unique spacing. A single crystal XRD or X-ray crystallography. In the single crystal crystallography, single crystal X-ray is diffracted by single crystal is a diffraction or non-destructive analytical technique which provides detailed information about the crystalline substance, including unit cell dimensions, bone lengths, bone angles, and details of site ordering. See, this is the X-ray, this is the crystal, and diffracted, and this diffracted crystal, this is the diffraction pattern, and electron density map, electron density, and this electron density is the atomic model. In an experiment, monochromatic beams of X-rays are found in single crystal, which is mounted on a gonometer. The gonometer Okay, in an experiment, monochromatic beams of X-rays are found on a single crystal which is mounted on goniometer. The goniometer allows crystal to be rotated at a precise angle. At its rotation, angle diffraction patterns are measured by using X-ray sensitive camera or detector. The two-dimensional diffraction patterns or images taken at all possible angles are converted into three-dimensional electron density map with the help of Fourier transformation, mathematical operation. The electron density gives the relative possible atoms present in a crystal. If quality of crystal is good, then the crystal diffracts X-rays well. In such case, position of atoms in crystal can be determined with high precision, resulting in high resolution crystal structure. Information that can be obtained from single XRD, position and arrangement of atoms present in crystal, crystallographic information such as unit cell, dimension, interpolar spacing, symmetry, nature of bone and angle. Powder XRD. Powder XRD is the diffraction is a rapid analytical techniques primarily used for phase identification of a crystalline material and can provide information on unit cell dimension. The analyzed material is finely ground, homogeneous, and average bulk composition is determined. If nanomaterial to be determined does not form a good quality single crystal but exists as powder, then it can be characterized powder XRD. Similar to single crystal XRD, a monochromatic beam of X-rays are focused on powder sample crystals which is mounted on goniometer. The goniometer allows sample to rotate at precise angle. At each rotation, angle diffraction intensity at 2 theta measured by using X-ray sensitive camera or detector. A diffractometer is a measuring instrument for analyzing the structure of material from the scattering pattern produced, which is a beam of radiation and particles interacts with it. X-ray is passed from this slit. This is the lead stop. This theta cylindrical camera. Information from powder XRD lattice parameters such as unit cell dimension and interplanar spacing, comparison of diffraction patterns known in sample with diffraction pattern of unknown sample, average gain or particle size using Skinner's formula, grain size k lambda over beta cos theta, k means Skinner's constant, k 0.9 for spherical crystal, lambda wavelength for X-ray use, theta diffraction angle, beta full width of half maximum intensity. Strain present in sample, beta total, beta C plus beta S, k lambda over beta cos theta per neta tan theta, neta intercept strain, d grain size. Small angle X-ray scattering SARCs, it is an analytical technique that measures the intensities of X-rays scattered by a sample as a function of scattering angle. Small angle X-ray scattering can be used for wide range materials from soft material like nanocomposites to pure nanomaterial and in both in liquid and gas phase. In these techniques, X-ray scattering intensity as a function of 2 theta is measured, which gives a new information of wide variety of the sample not obtained from the X-ray techniques. In SARCs, data are reported scattering intensity log I base versus magnitude of scattering vector Q. So modulus Q equal to 4 sine theta over lambda, theta is scattering angle wavelength of X-ray. Information that can obtain from SARC size in aggregation status sample, the scattering intensity of lower value of the Q is lower than 1 nanometer, close the Guinier approximation. I equal to I naught U EQ square RG square over 3. I naught is scattering intensity if theta equal to 0, RG is radius of gyration. Ln I equal to ln I naught minus Q square RG square over 3. The scattering at higher Q values, that is the Q in the range of 1 to 5 nanometer, looks different for different shape particles, and the size is 1 to 5 per nanometer. So this region gives information on particle, determination of average particle surface area, concentration in molecular weight for biological can also be made. Application of X-ray diffraction, determination of crystal structure, phase identification, transition, grain size, texture, stress, determination of thin film composition, industry identification, archaeological materials. Advantage of XRD, fast identification of materials, easy sample of preparation, computer-aided material identification, large library of known crystalline structure. Okay, thanks for watching. It's all about XRD. And request you all like, comment, share, and subscribe. Thank you for your patience. That is now. Bye bye. See you again.